Welcome to a lesson with Dr. Powell. Let's take a look at how we can write a statement like this one in terms of the symbols for all and exists. So this statement right here, you can kind of think about it as being a lot of logical ands, like this and this and this and this and this and this and so forth. Um, uh, are true at the same time. Exists, you can think of it as being lots of ors. Either this or this or this. At least one of these is true. There exists one of, of something that is true. Okay? So how can we use such symbols? So right here, given any epsilon greater than 0, so that means for all. Okay? So all epsilon greater than 0. So kind of we have lots of propositions that are indexed, each one by epsilon. All right. So we can say for all epsilon greater than 0. All right. And we write it like this with parentheses. This is kind of what we're indexing. And then what we put afterwards is kind of this big proposition that we're working with. All right. Now, what are we working with afterwards actually involves something else. Involves there exists. Okay, so again, we're going to use parentheses because we're indexing something else. We're indexing it by epsilons, and then we're going to be indexing by deltas. This time there exists a delta greater than 0. All right, so all deltas that work. Now, keep in mind, we can kind of think about this as epsilon is, so epsilon right here, we can think of it as being a real number. Okay, think of this as being is an element of, and here delta is a real number, positive. Okay, and such that what? So then we have a statement that has delta and epsilon that depends on this. So this is like this is kind of some kind of proposition here that depends on some delta and epsilon. Say okay, and maybe we can curve these epsilons, make them look more like that. Okay, so we have for all epsilon greater than 0, there exists a delta greater than 0 such that this proposition right here is true. Okay, now we can maybe write this with the Boolean algebraic symbol as well, that proposition if we like, because we notice there's an if-then statement. If-thens can be written as a conditional. So we put a big parenthesis, and then we could say maybe a little parenthesis here, opposite of x minus a less than delta, then we put a conditional, then we can write, let's see, opposite value of f of x minus L is less than epsilon. Okay, maybe a big parenthesis there. Okay, there we go. So we've rewritten this statement using the for all symbol and the exists. So basically what we're doing is we're anding together all of these guys, okay, and then notice that all of these right here, all these propositions change depending on what epsilon is, but these propositions themselves, this is like an infinite union. So this is like a infinite intersection, and we're intersecting unions, all right? And this is a big union statement. At least one of these guys is true. All right. That's kind of helpful if we want to use De Morgan's law in order to negate such an expression that has for alls and exists. It's really everything flips upside down, so intersections change to unions, and unions change to intersections, ands, ors, ands, they'll swap places, and then you negate what's in here. Now keep in mind, this doesn't negate, and neither does this, because this is just indexing our propositions, like indexing what term we're at when we're anding. This just indexes what term we're at when we're oring. The terms themselves don't change. It's at least the position of where they are. You just have the actual terms are right here, and these are what are going to be negated. But the position of where it's at is not negated. Just what the proposition is negated. So coming along, if we were to actually negate the statement, what would that look like? That would look like as follows. That would look like so running De Morgan's through everything. Okay, that would be, so we're going to negate this. This would become an exists. So we have exists epsilon greater than 0. So epsilon greater than 0 is still there, but that changes. Then over here, that would be for all delta greater than 0. And then over here, you negate this statement right here. Now, the negation of this, you could of a conditional like this, we can think of, well, let's think of this as being like, for instance, maybe this is P and this is Q. So if you think about that P arrow Q, that's the same thing as saying, well, either this is false or that is true. So you could say not P or Q. That's what makes the arrow work. But if we want to take a complement of that, it's easier to see now what's going to happen. We're going to get P and not Q. So we could even write that in if you wanted to. You could write, so the negation, let's see. Yeah, so then that would mean just simply this part right here. So we have x minus a is less than delta. And then we can say, and, so meaning the hypothesis is satisfied, but the conclusion is not. And so, and if we're actually thinking about the calculus interpretation of this, what this means here, we're meaning that x is within delta of a, but what's going to be happening now is that f of x is not so close to what we want it to be getting close to in a limit. So this would be, so we could write the negation of this statement, which is absolute value of f of x minus L is greater than epsilon. And, okay, I kind of think about that. So we have, there exists some epsilon such that no matter what delta we pick, if we're within a of delta, then being within delta of a, we're also, unfortunately, we're going to be bigger than epsilon. All right, so we just kind of went through that idea of how to negate an expression with Forall and epsilon, and also how to take a statement like this and rewrite it in terms of this Forall and this exists. So in terms of Forall and exists. All right. Thanks for watching.